Hey, welcome. Every single time you turn on a tap, you're actually at the very end of this incredible hidden journey. I'm talking about a journey that takes water from the wild, puts it through a whole gauntlet of tests and treatments, all just to get to your glass. So let's dive in and follow this epic trek from start to finish.
Think about it. It's something we do every single day, right? We don't even give it a second thought. But the system that makes it happen? It's a total marvel of engineering and science. So what really goes on between, say, a river and your kitchen sink? Well, let's follow the water and find out.
All right, so where does this whole thing even start? Well, long before it ever sees the inside of a pipe, our water has to be collected from the natural world. Let's go right back to the beginning, right to the source.
Okay, so broadly speaking, our water comes from one of two main places. First, you've got the obvious stuff, right? The surface sources. We're talking lakes, rivers, reservoirs, the water we can actually see. But then there's this huge hidden source, all the water that's underground. And that's where things like wells and springs come in. And this brings us to a really key concept, the aquifer. Now, the easiest way to think about an aquifer is like a giant, natural, underground sponge. Seriously, it's made of rock and sand, and it holds these massive amounts of groundwater. Some of these sponges are pretty close to the surface. We call those unconfined aquifers, but others are way deeper, trapped between layers of solid rock. And you guessed it, those are the confined ones.
And this is exactly how we get to that water. A shallow well? That's basically just dipping a straw into that top-level unconfined aquifer. But a deep well, that's a whole other game. It has to drill right through a layer of rock to reach that deeper, confined aquifer. And the water down there, it's usually much purer because it's been naturally filtered and protected from all the gunk on the surface.
Okay, so we've collected the raw water, but is it safe? Can we drink it? Nope, not yet, not even close. Before that water gets anywhere near our homes, it has to survive a whole series of super tough tests. I like to call it the purity gauntlet.
So what exactly makes water good? Well, this is basically the checklist, the greatest hits of high-quality water. We all want it to be clear and sparkling, nice and cool, and of course, have no weird taste or smell. But behind the scenes, there's a lot more going on. Scientists are making sure it's free from nasty pathogens, that it won't corrode our pipes, that it's soft and has a neutral pH. It's a really specific recipe for the perfect glass of water.
And it goes without saying, not all water sources are created equal. You can kind of think of it like a risk assessment. Water from those deep, protected wells, that's considered wholesome. It's almost good to go. But what about stored rainwater or water from farmland? That's suspicious. It might have runoff, so it needs a much closer look. And then you have river water that's had sewage access. That's straight up dangerous and needs the most intense treatment of all.
So, how do they measure all this stuff? Well, they run a whole battery of tests. Take color, for instance. There's actually a maximum permissible limit, and it's 20 parts per million. And this isn't just about how it looks. Color can actually be a sign that there are dissolved substances in the water, like from decaying leaves or something.
And then there's a test for something called turbidity. It's really just a fancy word for cloudiness, It's caused by tiny little suspended particles, like silt or clay. And for this, the limit is even stricter. We're talking just 5 to 10 parts per million. This is all to make sure the water that finally gets to you is absolutely crystal clear. All right, so the water is clean, it's clear, we're good to go, right? Well, not quite. There's another really common problem that needs solving, and that's its hardness. This is a huge deal, and it has to be taken care of before that water is ready for our homes.
You've probably seen this yourself. If you've ever noticed that chalky white scale building up in your kettle, or been frustrated because your soap just won't lather up properly, yep, you've experienced hard water. It's all caused by dissolved minerals, specifically calcium and magnesium, that the water picked up somewhere along its journey.
But get this, it turns out not all hardness is the same. There are actually two types. First, there's temporary hardness. This is caused by bicarbonates, and you can actually get rid of it just by boiling the water. That scale in your kettle, that's temporary hardness literally coming out of the water. Then you have permanent hardness. This stuff is way tougher. It's caused by things like sulfates and chlorides, and you can't boil it away. And what's worse, this kind can actually corrode your pipes.
So how do the pros at a water treatment plant deal with this? Well, for that temporary hardness, there are two main tricks. Boiling works, but obviously only on a small scale. For a whole city supply, they use something called Clark's process. They add just the right amount of lime, which basically forces those dissolved minerals to turn into solid little particles. And once they're solid, you can just filter them right out. Pretty clever, huh? But what about that stubborn, permanent hardness? For that, they've got an even smarter trick up their sleeve, called the base exchange process. So the water flows through a tank full of this stuff called zeolite, and the zeolite acts like a super selective filter. It grabs onto the hard minerals, the calcium and magnesium, and swaps them out for harmless sodium. It's a simple exchange, and just like that, the problem is solved.
Okay, so at this point, our water has been sourced, it's been tested, and it's been treated. It is finally ready for the last leg of its journey, the massive, complex network of pipes that's going to deliver it right to our homes.
And this quote right here points to a really key idea in modern water delivery, the grid system. The advantage of a grid is just huge. Think about it. In an older system, if one pipe breaks, everyone downstream is out of luck. But with a grid, you can just shut down one little section and reroute the water around it. It makes the whole system so much more resilient.
Now, once the water actually gets inside your building, there are two main ways it's handled. You've got the direct system, which gives you high pressure straight from the mains. That's what you want for a powerful shower. The other option is an indirect system, which uses a storage cistern or tank. The big pro there is you have a reserve supply if the main line has a problem. But there's a trade-off, of course. The direct system comes with a small risk of something called back siphonage, while the indirect system has lower pressure. It's a classic engineering choice, power versus reliability.
And there you have it. From a distant source like a lake or a deep aquifer, through that whole purity gauntlet and all the treatments, and then through miles and miles of pipes, your water completes this absolutely incredible journey every single day just to get to you.
And that really leaves us with a final, important question. This entire system is amazing, but it's also largely invisible. And let's be honest, we all kind of take it for granted. It depends on protected sources, on infrastructure that's getting older by the day, and on constant monitoring. So the real question is, are we doing enough to protect this vital, hidden journey? It's definitely something to think about the next time you pour a glass of water. Thanks for joining me on this one.